Right, good morning. So the only reminder for you, like last time, is about your lab number 1. And submission will be due basically next week, Monday, so slightly less than a week. I hope everybody got at least started, right, with the rodent, okay? I will highly encourage you to at least try some part of the exercise on the remote lab, because that's gonna be the working environments for yours coming programming test. I'll make sure I give you some practice questions as well, don't worry, but I'm saying that you wanna gain the experience before that. And tutorial video, really take your time to really take any additional notes. I did make the iPad notes available to you, but take your own notes if necessary. And the problems to solve, really focus on them. And I will be in your lab session this afternoon. I think immediately after the class. I'll be there at least for 10 or 15 minutes. If you got a question, please catch me earlier. Otherwise, you can see me in the office hour. Either way works, but at least one TA will be there. And for the math review lecture, I don't think we will be able to finish today because that's really important material. I want to make sure everybody's okay. So maybe today and a good part of Thursday. And then we'll start with the bridge controller, which I kept talking about in the intro. Alrighty, let's now talk about some review, like a recap. Now, I think that'll be very valuable, so we can connect to what we need to talk about today. I think last time we basically talked about the strategies for proving or disproving universal versus existential properties. Just want to remember the rationale behind each of the strategy. Want to be very clear about them. And later on, when we talk about sets, functions, relations, we might just be able to use them sometimes. And also when we talk about bridge controller, FTP protocol later, you can also use them. All right. And example here, make sure you got it. And about conversion. And here, about the sets, I deliberately went a little bit quickly last time because I really wanted to cover the power set. But today, we can go back to the basic stuff about subset and etc. I'll give you some very useful connection to some software design problem. Okay, I will talk about it too. And we're going to do some exercise on the basic operation for sets, but you guys have to make sure you understand very well this particular page. When we talk about, number 1, how you're supposed to calculate the power set given a set systematically. Number 2, if I ask you about somehow to formulate the cardinality of certain power set, that's another way, right? Of course, there's another formula which I want to mention a little bit. I will revisit these two formulas and compare them. They are basically boiled down into the same thing. But this one here turns out to be a little bit more flexible for you to use. I'll talk about it, don't worry. All right, for today, I'll talk about this formula briefly as well, okay, just for your information. And for today, I want to start with some simple exercises together with you, just to make sure you're okay with the basics. Right? It's basically based on the slide over here, and about the set comprehension expression here, you will see a lot of examples in the slide as well. For example, when we define the basic operations, let's take one for example. If you, oh, sorry, not here just yet, but I'll show it to you later. So we need to understand very well about the subset over here, and also equal, and also proper subset. It's really important to note, right? Let's do some example together. And one thing to note here, you can see the way we define the subset relation over here is by using a universal quantification. S1 will be a subset of S2 if everything that's in S1 should also be in S2. You can see everything that's in S1 as the antecedents. It should be also in S2. What about anything that's outside S1? That will actually make the antecedent false, in which case we don't care, right? It's kind of go back to the connection to how we define implication. Right, let's do some exercises. You can definitely go over the definition. They're straightforward. Okay, let's go one by one here. Easy ones, but I think they can definitely illustrate certain points. The first one, very easy. About set membership. How do you rewrite this operation over here? For this one here, I'm not going to bother you too much. How can you rewrite it in terms of this and this? If I say E is not a member of S, I can definitely say it's equivalent to, it is not the case. E is in S. Sometimes it might be desirable to actually rewrite this notation here into this, so that you can focus more on this particular membership here to talk about. So that's why it will be useful. The first one, straightforward. And the second one here will take a little bit of thinking, but it's not too bad. We want to somehow find a common pattern of logic for us to define. Number one, how do we define numerical equality in terms of less than or equal to and larger than or equal to? Pattern should work for number one. The pattern should also work for number two, in which case we are trying to define the equality between two sets as opposed to equality between two numbers using subset equal over here, both ways. All right? Any suggestion about defining this? Let's start with the first one. If I got two numbers, how can I actually say the two numbers are equal to each other in terms of this? It's actually more straightforward thing. For example, let's say, I'll give you a little bit of hints. If you got 4 and 7, apparently these two numbers are not equal to each other because even though you got 4 less than or equal to 7, but it is not the case for larger than or equal to 7. This cannot be true at the same time, right? If these two are not true at the same time, that means they are different numbers. Okay? Apparently this is actually true, this is false, right? There's a little bit hints for you. How can we formulate this observation to have a pattern for this? Adrian?
Less than or equal to and greater than or equal to.
Yes, indeed. That's basically you want to say conjunction. It should be both. So what I will do is I'm going to formulate this to say, let's say for every x and y, right? Over here, let's say it is the case. Let's say x is an integer and y is an integer. And if x is equal to y, that should be the case that x larger than or equal to y and y larger than, also x smaller than or equal to y. It should be both at the same time. Right? Agree? That's just some common pattern you can use. Okay? And how do you use this pattern here also for this? Set equality. Right? What you got to do is, using the same pattern over here, all you got to do is x and y, rather than using just integer, they can be just like a set. Okay, let me write it down here. So for this one here, what you can do is something even simpler. S will be t. That implies S a subset of t, and also S is also a superset of t at the same time. Right? Of course, you can definitely argue the other direction is also true. But I'm just trying to make the pattern very similar. So what you should really learn from this one here is to get comfortable about using universal quantifier to really specify what you really need. That's really important, especially when we need to define relational operations later today. Okay. And this one here is also very interesting. Okay. Let me highlight this. What I'm going to do is, after going over a little bit more exercises over here, I'm going to give you some connection to how I can apply that to software design a little bit. I'll do that, but just bear in mind. That's something we're going to do later. Okay? And two more exercises. And this table here, I'm going to fill out maybe a little bit with you, and you can do the rest. Very straightforward. You basically consider all the definition, all the combinations. The way to read it is like this. We got S here, we got T here, and also we got U over here. Okay? And now, first of all, S is a subset of S. Think about this part over here is the left-hand side. This part over here is the right-hand side. Let's have that convention so you will see how to interpret. Let's say this part over here will be the left-hand side of the operator. Let's say this part over here will be the right-hand side. So we got all the combinations. Oh, let me just draw a bit better. And this part over here will be the right-hand side. Okay, let's do a few get a feeling about it. When I say, let's say here, S is a subset of itself. Is it true or false? Always true. Always. Very good. Doesn't matter what S is. In this way, you don't even need to look at this. What about S being a proper subset of itself? That should be false, because if you think about it, think about the definition. If you go back to the definition over here, we say that if S1 is a proper subset of the other, not only that the new S1 should be a subset, but also the cardinality must be strictly smaller. How can the cardinality of S to be smaller than itself? It cannot be. So that's why it will be false automatically. All right, so once we are done with this, we can easily fill it out a bit more. You can see we do T and T, and also U and U, right? So this will be true, this will be false. Also, this will be true, this will be false. All right? Hopefully you're following. The diagonal will be the same. Let's now do maybe a few more. What about, let's say, S and T? Let's do this one here, okay? So this is the one we want to do over here, okay? So now, S, a subset of T. S, a subset of T. Is it the case? Yes, indeed. Just the order is a bit different, right? Okay, good. Thank you. So that will be true. What about S, a proper subset of T? No, because they have the same size. One needs to be strictly smaller than the other. Okay, false. Okay, you guys got the idea, right? How about this? I will give you the solution. Maybe when I post the notes, I'll write it down myself. But I would suggest take a look at, draw the table yourself and figure out the answer and check. Okay, we can save some time in class, but that should be very straightforward. If there's any entry when you look at the solution that's not clear, let me know. That should be very straightforward. Okay, exercise. I'll make sure you got a solution when you see the iPad notes later tonight or tomorrow morning. Okay. Now, a final question. Here we have something called set difference. So when you say S, a set, and also you got T, another set. And how do you write set difference? You can either write this, or you can just write a minus. I think either way will be acceptable, okay, on the paper. But for rodent, of course, you got to make sure you write exactly what is required. Let's say I keep this one. That's actually on the slides. Do you guys know the word commutative over here? What does it really mean to be commutative? That means doesn't matter the order in which you apply the operands. Addition plus will be commutative because A plus B is the same as B plus A, also for multiplication. So now, for set difference, is it commutative in general? No, actually, but that's okay. You know, let's say in case I give you this question on the test, right? It's more like a universal quantification. I'm saying for any two sets, they are commutative in terms of set difference. If you want to disprove it, what do you have to do? You got to give me one counter example where set S minus T is different from set T minus S. That's the witness you have to give, right? So the answer is no. In general, this is not equal to T set difference S in general. And for this one, let's do some example quickly together. Okay, let's find this one here S, and also let's say this. I want to calculate S difference U, and also U difference S. Right? You can see the S over here and the U over here. Okay, and to make it a bit more visual for you, and then I'll explain that. That's what we got here. You pretty much know about the standard diagram here. Let's say I put S over here, I put U over here, okay? And what's really the intersection between the two? 2 and 3, agree? 2 and 3, that's the intersection. And what will be this part over here? This part here is whatever that's in S, but not in U. 1. Apparently, right? 1. So this is basically whatever that's in S, but not in U. What about the other way? Whatever that's in U, but not in S. Nothing. How do we say nothing? Empty set, exactly. Okay? So I should really say 1 here, and let me use a slightly different color here just to show to you so you see both. So this will be empty, which would be whatever is in U, but not in S. Right, so these are just basic, just to get yourself comfortable and back to the mood for the various set operations. We'll see more application later. Are we okay with this? We're good? All right. All right, I want to do a quick example showing to you what we are learning now, basically what you learned in the previous 1090. Some very basic property can be applied to software design. I'll give you a little bit of idea about how you can do it. Let me give you the context. Let's say you're trying to define a method called all positive. Okay? It's going to take a set and return a set. I'm just using the hash set, for example. But I can think about the hash set in Java at the abstract level. Think of it like more like a mathematical set that we talk about. Okay? What does it do? It's going to return the set of positive elements from the input. Let's say, for example, if I got my input that looks like this, let's say 2, 3, minus 1, 4, and minus 2. Right? In that case, if you say all positive and call that upon the input, it's just going to filter out anything that's not positive. You're going to filter out this, and it's going to give to you 2, 3, and 4. Right? That's a very quick example. At least you know what it is doing. All right? This is actually a very general problem you have to face, a very fundamental method maybe you have to define all the time. Given a collection, you want to return just another sub-collection such that you're only going to keep all the elements in the input collection that satisfy certain property. In this case, the property we're talking about is being positive. Okay, we okay with that? So I'll leave it to you later after I discuss this example fully to really apply that to other property, right? And the question goes like this. Let's solve it together. We want to formulate this method here using a set comprehension. Oh, there are 2 things. Number 1 is set comprehension. How do you express this all positive over here in terms of set comprehension? What I want you to do is something like, I'll let you think about, I'll give you some skeleton. If I say all positive, and then any input, which is a set of integer, and I'm trying to formulate. Think about this equality here is I'm going to formulate what is going to be equal to at the abstract level. And on the right-hand side, I want you to put a set comprehension notation. So this will be some nice practice for you to do set comprehension. This was really easy. That's the first part. I got another part of question for you. Anyone? Feel free to try. It's okay to be wrong. Adnan, go ahead. Mm-hmm. Yep. Okay, I tell you what. Very good, Adnan. Let me write down what you said. Sorry, say it again. Could be incomplete, right? Very good. So guys, question for you. It's very important to see. If this is the answer, is it really correct? Intuitively, it's not really correct, but can anybody explain why it's not complete? Mm-hmm. Because here x, though it's positive, let's say the input is this, right? Let's say rather than returning 2, 3, and 4 to you, like this, I might just return, for example, 1, 23, and also 46. It's also all positive, but is it really the correct result? Not really. So this so-called specification is not complete. All right? It's really important to learn from this more than when I give you the complete answer. Okay? This is not good. Okay? And this one here, alone, not complete. So what you really have to add is another conjunction. Right? So you want to say, and X should be a member of the input, which is a set. So this will be a nice warm-up for the second part of the exercise. Ryan.
Would you say for all X in input?
Here, actually, there's no for all, right? It's a set comprehension. So for the set comprehension expression here, just remember to the left of the vertical bar over here, you don't put any like a constraint. You only put like a list of variables or some form of the variables. And you put all the constraints on the right-hand side. So the syntax is a little bit different from universal versus existential quantification, right? It's a little bit different, yeah. Are we okay with the first one? Good. Second one. The same method here, but now we want to argue something about, okay, so this is something, I'm not too sure if your professor will talk about in 3311, but normally I do. So this is something called post-condition. So people usually talk about when you want to design your routine or function for your software module, you have to think about its precondition and post-condition. What would be the precondition, for example, for binary search? Do you guys remember from 2011? What should be the precondition? Without a precondition, binary search cannot work.
The list is in order.
The list is sorted in order, exactly. Okay, very good. That's just one example. But what we are talking about here is post-condition. Post-condition says the following. If the precondition for your routine or method is satisfied, you execute the implementation or body of the method, what should be satisfied? Okay? And now we want to be a little bit more formal about this. But how do we do that? Okay? So let's say this. I'll give you a little bit hints. So here's a problem. Let's say this is the input. Let me be very careful about the color I'm using. Okay, let's say this is input, right? Let's say this set over here is the input set. And let's say we can conceptually partition the input into two partitions. This part here is called S, where all the element is simply positive. Another part, the other part is less than or equal to 0. Imaginary partition. And we want to somehow say this particular partition here should be exactly equal to whatever that's returned from the method. Agree? That's how we can make the post condition more formal and complete. But let me write it down and then I'll recap. So what we want to have is for the return value over here, let's say that one there is basically another hash set that's returned. Think about this is the output. So what we really want to specify is this guy over here and this guy over here, they are equal. Let me recap. The post condition, to really put it formal, you have to somehow say this. The return value for this method here is a set. That one there should be exactly equal to part of the input. That is larger than 0. No more and no less. All right? But now, the question is, how do we formulate the equality between these two sets? That's the question. I'll give you guys maybe 1 minute to think a little bit about what predicate or what subset relationship you may want to use. Think about it. It's actually quite a nice illustration about how you can really think mathematically. And if you really want to write some JUnit test, let's say to test your software, you want to test both. Okay. Now, of course, in this course, we try to prove, not really to write JUnit test. Guys, take maybe a moment, 30 seconds or so. Think about what you may write. This could be maybe exam question. Could be. Right? Of course, at this point, if you really have no clue, that might suggest you may have to review a little bit more about the basics, because this is really something I would expect you guys to be able to do, for sure. Okay? Yeah, one moment. There are different ways to write this, at least two ways I can see. So, all right, just one moment, and then I'll see if you got any thoughts. I'll mention both solution to you. One way is just use set relation, just use set operator. The other one is by using predicate logic operators only. I'll show you both versions. You can learn from both. Yes, go ahead. Okay, I see what you mean. You want to take the set difference between, for example, you mean this one here, set difference this, you should really get this. That's a nice idea, but it's a little bit indirect. I like that idea, but there could be a way to be more direct. Okay, you're also trying to use set difference. I would say when you try to use the set difference, it's a little bit indirect because you're saying that everything that's here but not here. This is an easier way. Yes, I'll take one more. Yes. That's brilliant. I agree. Yes. That's very good. That's the first version. That's easy. Right? So what you guys can say will be version number 1. Okay, you can say the output is a subset of S. There's partition here. And also S is also a subset of the output. Because both together can tell you S will be equal to the output. Both are important. Okay? Let me say a little bit more and then I'll take your question. When we say this, we're saying that everything that's in the output should be in S, right? So we don't include anything in the output that's actually not even here, number 1. Number 2, when we say this is a subset of this, the easiest way to put it would be we didn't miss any elements from here. Everything's in the output, okay? It would be very important for you guys to know both are required. If you miss any one of them, you'll be in trouble. That's why when we say formal specification, it should be complete. Let me go a little bit further, and I'll give you version number 2. Let's call this post condition number 1, post condition number 2. Okay, let's talk about the evaluation. Okay, number 1, what if only P1 is required? Then let's say we don't have P2 for now. If only P1 is required, in that way, are we going to allow any illegal scenario to occur? What is that? If we only require that output is a subset of S, then what's wrong with that? So, yes. So in this case, for example, output could be just empty set, right? Agree? Because you can easily say output is empty. In that case, everything that's in the empty set is also here. In that way, you're not returning something very useful. Agree? Okay? So that's one example. For example, empty set can satisfy P1. Okay? And the second one. What if only P2 is required? This one might be easier to contradict. Let's say we don't have P1 over here. We only have P2, which is to say everything that's here is actually already in the output. Isn't that already complete itself or no? I heard no. Why? Yeah. They are not really here, exactly. Okay. So, for example, output contains elements that is not in S. That's kind of the example I gave to you over here. The output contains all the elements, even though they are positive, but they're not exactly in the original input. That's basically what I talk about. All right, guys, I think that's kind of important. Really think it through, okay? All right, that's version 1. Let's do version 2 very quickly by using predicates. And I'm going to start a new page. Okay, what I want to do is I want to still keep this diagram here handy, and then I'll write it down, and then we can move on. Okay, over here. Now, how do we specify using predicate, right? Which will be equivalent to using set relation. We want to do both direction. Let's do this one here. Everything that's here should be here as well. So, yeah, I just want to make it, oh, you know what? Let me do something that's corresponding to this. Okay? Let's say everything in the output is also in S. Let's say that first. Okay? So I can say for every X, if X is in the output, that implies over here, you can either say X is really in S, but in this case, we know that it should really satisfy this particular property. So you can also say X is larger than 0. That's also fine, okay, for this one here. And for property number 2, we want to argue the other way. P1 is about whatever that's in this also satisfy this. P2 is going to be whatever that's in here is also included over here. So you want to say for every X such that you can say X is in the original set and the original set which is input. And also X is larger than 0. Of course, this one here is equivalent to say X is in S. That's imaginary. That implies X is in the output. The main reason I'm trying to show you so many alternatives and also discussed, I really want you to get comfortable about communicating ideas using math. That's really what you need for this course. All right? We'll do more as we go. Any question about this example here? Think about it. If there's any part that's bothering you, you should really talk to us. All right? Go ahead. Okay. What you're saying is something like this. You're basically saying something like, if and only if, that's what you meant, right? I would say logically, that's really good. I would say on the paper, not bad, it's good. However, you will have a little bit of trouble of putting this into Rodin, because Rodin will require you to have the implication sign over there. So just considering how you can tool support this. So I would say this is good on the paper, nothing wrong with it, but maybe you want to avoid that because it may not be so direct translation into Rodin. Yeah, okay. Valid on paper, but inconvenient. How about that? Inconvenient to put into Rodin, which could be a concern if you want to do that on the programming test, right? All right. If everything is good, let's now move on. I've talked about this, I've talked about that, and then the next one will be, okay, let me do one more, and then we're going to take a short break, and then we can move on to the next topic. Okay. And, okay, this one is easy. Okay, guys, very quickly. So what set always holds? When you actually put on the left-hand side, what set is always a subset of S itself. That one's easy, okay? That one I shouldn't bother you too much. And also empty set, right? Because empty set is a subset of every set, right? That one's easy. And what should I put over here? Something that always fails. Of course. That's something we also illustrated, right? And this one here, for some holds for some S and fails for some S. Whenever you find this kind of tricky property, most likely it's going to be the extreme case. As I would say, empty set is a very good guess, or the set itself. So it turns out this would just be the empty set. But why? Right? Let's put it here. Yeah, let me put it down for you. Okay. So think about empty set, proper subset of S. Okay? It could be true if S is not empty. Its cardinality is larger than 0, right? Because empty set is guaranteed to be of cardinality 0, which is strictly less than that. Okay? It will be false if it is an empty set, because empty set is actually false. That's why the result depends. Okay. Okay, and then this one here, you guys can think about, if I say S1 equals S2, does it imply S1 is a subset of S2? That one for sure, right? But the other way around is not the case, right? Why is that? If I say S1 is a subset of S2, it does not necessarily entail S1 is S2. Yes?
Because if S1 is a proper subset of S2.
Exactly. You're getting it. Very good. Okay. So you can see, for example, if you got S1 here, and also S2 over here. In this case, S1 is a proper subset of S2. At the same time, S1 is also a subset of S2. Both are true. Both are actually true. But this one over here does not really imply that S1 is simply equal to S2. It does not. In order to really show it, you also have to show that S2 is also a subset of S1. But according to this setting over here, it's not the case, because S2 is strictly bigger than S1. Okay? Yep. I think many times visualization will definitely help. Okay, done. Okay, so what I would do is, let's see, union intersection difference. Yeah, very easy for union intersection. And power set we talked about last time, and that's what we did. And little exercise for you. Okay, you can give it a try. And before I talk about this, let me review the formula quickly, and then we'll talk about, I'll take a short break, and we'll talk about relations. Okay, here. Right, we talk about cardinality of power set. If you recall this little page that we did last time over here. Okay, this formula over here. Assuming that you already study a little bit with it, let me go from there. Compare a little bit. Okay? There are two ways for you to think about how to compute the cardinality of power set. I will mention both, and then you decide which one you're going to use. Okay? Approach number one. By considering subsets of various cardinality. Okay? So you can think about in this way. If I want to calculate the cardinality of the power set of, let's say, a set S, right? It's going to be, number one, how many subsets are there for cardinality 0, right? In that way, we're going to choose from this many elements from the set. How many do we choose for empty set? Choose 0 elements, okay? Plus, choose also 1. I'll annotate a little bit very soon. Okay, so basically think about this guy here is the number of subsets of cardinality 0. And of course, it is the property of the choose operator. This one here would always be just 1. That's a special case, right? And what about the number of subsets of cardinality 1? This is also a special case. It would be just S, right? For example, if you got, let's say, A, B, and C, what would be the subsets of cardinality 1? Either A or B or C, right? That was easy to illustrate. Okay, either A or B or C. And the final one here, choose this many elements from the original set, so to include everything. So it's a maximum subset. Number of maximum. One here, 1. Of course, you got many things in between. The advantage of understanding the calculation this way is if I simply asked you, how many subsets do you have in the power set that's of cardinality between maybe A and B? I'll write it down for you. For example, flexible calculation, flexible, okay? For example, how many subsets of cardinality between some lower bound and upper bound? For example, how many subsets are there whose cardinality are between 2 and 4? In that case, you got to use the choose operator 3 times. Choose 2, choose 3, and choose 4. Agree? Guys, are you following me? Or maybe I need to be a little bit more explicit. You okay, right? If you need me to do more illustration, please just raise your hand. I'll just do that. Otherwise, I assume you're okay. Okay? All right. So this one here is actually a little bit more flexible for you to calculate individual category of subsets of certain cardinality, right? That's one way to look at it. Another way to look at it would be something also I'm pretty sure you know about, but let's talk about it. And this one over here, okay? This will be simply 2 to the power of S. That's it, right? And what's the insight into this formula here? Adnan. It's exponential for sure, but why? Oh. So think about this. Don't worry. I'm gonna just go. I'm pretty sure you guys have heard about it. Let's say, for example, let's say if I have a set S. Let's say A, B, and C. One way to think about it is to turn this into like a binary number. Okay, let's say we got A here. Let's say we got A here, B here, and C here. For every element or for every member in the set, we got 2 possibilities. Either to include it or not to include it, right? So if you try to do the binary number, it's going to be something like this. If you say 0, 0, 0, that means you don't include any one of them. That will correspond to the subset empty set, right? If I do 0, 0, 1, it's going to be the subset just C. That's just another way to systematically enumerate all the subset. And if you go all the way, what will be the last one? 1, 1, 1. All right, guys, you know what I mean here, right? All right, that's another way to interpret the formula, right? All right, any question so far? I just want to revisit the formula. So whichever you need, you can just use it, okay? Good. Any confusion about the formula, please let me know, and then we can talk a little bit more, okay? Okay, I would suggest we take a little break, and then by taking attendance, and then we'll talk about relations. Okay, you definitely need lots of brain power fresh for that. Okay, get yourself ready for iClicker on your mobile phone, please, and then we'll do that. And you guys can take a short break. Okay, I'll start a poll. And then, select. Yeah, check in, please. Does it work? If it doesn't work, guys, please don't waste time. Just come over to the front, and then I got a sign-up sheet for you, please. All right, anyone still trying? Otherwise, I'm going to close the poll. Everybody okay? All right. I'm going to close it now, and then it's now, according to my clock, 12:16. Take about 3 minutes break. Don't go too far. All right? If you got trouble, you want to sign up, come to the front. Doesn't work? Okay, so let's see. Do you have a pen by any chance? Yeah. Yes. Yeah, it's sorted by last name. Find your name, and then please check and sign. Okay, find your. Oh, there's another one on the next page, just in case. There we go. Yeah, if you can sign, please. Yeah.
Sign?
Sign, yeah. Thank you. Question?
Yeah, for the set different, does it has to be the backslash? Or can this direction? I don't really
No,
sure.
you got to be backslash. Yeah, either do backslash or do minus. Either way, on the paper. All right, guys, take about 1 minute or so, and then we shall resume. All right, just one more moment, and we should get started. Alrighty, let's get started again. So we are now done with the review on the basic sets, but we're going to build on top to define what a relation is. And I think the next 10 minutes or so will be the most important to really get a feeling about what relation is. I can tell you right away, what's really a relation is a common confusion. A relation is just a set of pairs. That's all you need to remember or memorize. Just remember that principle. Otherwise, you might just get confused by so many symbols or so many operations. Remember, a relation is just a set of pairs. But we're going to define that formally. Let's take a look. All right. The relation definition will be in the next slide. We're going to build on top of that. Okay. But before that, let's talk about tuples. I'll show you the definition over here first, okay? So let's say we got set number 1, set number 2, all the way to set number n. We got n sets, okay? And then we have the notion so-called cross or Cartesian product. I'm pretty sure you heard about the term before. But let's now revisit its definition. We need this for defining relation. But for the relation, it's a special case where you only got n is equal to 2. You only got S1 and S2. Luckily, you only got to consider just 2 sets, but just in general. And we talk about n tuple. If you actually got element 1, element 2, all the way to element n. Of course, in the case of relation, it's going to be element 1, element 2. Okay, special case. And let's look at this definition here, and we'll do one example just to make sure it's clear to you. Let's now take a look at the definition, and then we'll do one example together. Okay, n tuple over here. What is that? Oh, this is over here a set comprehension notation. All right, but to the left of the vertical bar here, we got something that looks funny. What we had before was something like maybe all x such that there is some property that x should satisfy, right? So now, rather than just a single variable x, we got something very funny over here. That seems to be n different kind of stuff. This is allowed in set comprehension. You want to remember the left-hand side over here for the set comprehension. When I say left-hand side, I meant the left-hand side of the vertical bar. This one here really specifies the structure of each member in the resulting set. The structure of each member in the resulting set. We are saying that every element in the resulting set is going to be more like a tuple. We wouldn't say it's a pair. Usually pair is only for 2 elements. But in general, you can have element 1, element 2, all the way to element n element. So that's why we call it n tuple. Okay? And how should we construct such n tuple? And then we'll do one example. Each of the element here should be in its corresponding set. For example, E1 over here should be a member of set number 1. Right? You can see set number 1 over here. And also, E element number 2 should be a member of set number 2, which is set number 2 over here, and etc. Right? That's what this is trying to say. Don't be too terrified by the math. You just make it precise for you. All right? Based on this, we can easily calculate cross product. Okay, let's take a look. Okay? Let me try to apply the definition for you, and let's go a little bit deeper into it. Okay? So let's say we want to calculate, let me write it down again, AB cross product 2, 4. Cross product dollar and %. Think about this guy over here is the S1. This guy here will be S2. This one over here will be S3. Straightforward? And let's now apply the definition, just make it clear. By definition, it's going to be E1, E2, E3. Because we got 3 sets, so only E1, E2, E3. It's a triple. Okay. So we're going to get E1, E2, E3. Now, guys, how do I complete the rest? Any suggestion? We want to get all the E1, E2, E3 as a triple. But what should be the property for E1, E2, and E3? For example, E1. E1 should be a member of S1, yes, which in this case AB. S1 doesn't really exist in this context. I just annotate that so you know it's actually linking to the definition. So what you're really supposed to write would be E1 is a member of AB. And E2 is a member of 2, 4. And E3 is a member of dollar and %. Right? That's how you write precisely. You got 1, 2, and 3 over here. And this part here is the structure of each element. All right? And of course, let's have a little bit of anticipation. It's going to be a big set with how many members? Well, thinking this way, right? You gotta use this kind of a permutation concept very often. E1 can be any of the two. E2 can be any of the two. E3 can be any of the two. So 2 times 2 times 2, which will be 8. However, I happen to choose the cardinality of just 2 over here. It could be 3, could be 4, right? It depends, okay? I can do a little bit of formula over here for you. If you think about, if I got S1 multiply S2 multiply all the way to Sn, what will be the resulting cardinality? It will be easy. S1 multiply S2 multiply all the way to Sn, right? There will be actually quite a good number of formulas and definition after we complete the review lecture. If you look at individual of them in isolation, it looks straightforward. But put everything together, you might just get confused. That's why you really got to study and connect the dots. All right. And just to note to you, this is cross product, right? And this guy here is multiplication. It's very interesting. You put the cardinality here overall. It could be broken down into individual cardinality. Right? Think about it. Very fun. All right. So now there will be 8 in total. Of course, it will be up to your personal preference about how to enumerate them. I do have a personal tip for you. Feel free to follow it or ignore that. But you have your way to actually enumerate if I ask you for that, okay? This is how I usually do it, in case I cannot just enumerate comfortably right away on the fly. Think about we're going to have basically E1 and also E2 and also E3, right? I'm gonna draw a tree. Starting from here, what can be E1? A or B, thank you. A or B. And for each one of them, I'm going to consider what could be E2, 2 or 4. So here, 2 or 4. 2 or 4. I'm pretty sure you know what I'm doing here. And then from here, what could be E3? You got to consider for every one of them over here, each one of them will be either dollar or $n%, dollar or $n%, dollar or $n%, dollar or $n%. And now, how do I systematically enumerate them? Think about the path from root to the leaf. A2 dollar will be 1. A4, oh, sorry. You got to be very careful, actually. A2 $n% will be 1, right? And etc. So this one here would be like a A2. Oh, actually, be careful. Each one of them is going to follow this structure here. So it will be A2 dollar. And this second one over here will be A2 $n%, and etc. Now you can see all 8 because you got how many leaves? 1, 2, 3, 4, 5, 6, 7, 8. That's one way to fill out the blank over here. You can follow it, but if you got a better way for yourself, keep it, no problem. I'm just showing you one way, okay? And exercise to make sure you actually finish that, right? Make sure you can do it. All right, any question about cross product? Building on top of cross product, we're gonna define relation, all right? We're good. All right, let me now move on to relation. Relation is basically going to add on top the concept of power set on cross product. That's why things can get a little bit weird, but let's try. A relation is a set of mappings. When I say mappings over here, it's like a pair. You may want to go from A to B, A to C, and etc. Just a pair. Okay, that's what I meant by mappings. Each mapping is an order pair, right? From A to B, B to C, the order does matter. Later on, when we talk about relation and function, we talk about domain versus range. So that's why they could be of different types. So the order of the pair does matter. That maps a member of set S to a member of set T. Okay, let's now, before I formulate it about what is the set of all possible relations, there's an important concept over there. Before that, let's just talk about based on this definition, right? Every relation is going to be a set of pairs, just a set, right? A set, so important. So given S and given T, right? Let me do a little bit of exercise with you in the beginning. It's so important, okay? This is what you want to keep in mind. And guess what? This is nicely connects to your lab number 1, right? We use sets and relation. For your lab number 2, which I'm going to release next week, is going to go further about some tricky problem, interesting problem to solve using sets and relations. We'll definitely let you practice, okay? Okay, so let's now talk about, first of all, relation is a set of pairs. And let's say, for example, a relation on 2 sets. Let me recall myself. 1, 2, 3, and AB. Okay. And you can think about this is S1, this is S2. S1 and also S2. All right, these two. All right, let's do some very basic check. Number 1 is a relation on, I'll say S1 and S2. Think very carefully. I mean every character I wrote. Is 1A a relation on S1 and S2? And you got everything you need, even the first line that tells you the definition. Yes? Okay. It's okay to say yes. No, don't feel bad about it. It's not a set, exactly. Guys, it's a category error. By definition, a relation should be a set. Is 1A even a set? No. Don't be too surprised if I give you this on the written test. And if you ask me if there's any typo, I would say there's no typo. All right? Be careful. It's so important to actually understand what's really going on here. That's why I want to give you the common error that your maybe previous classmate kind of suffered. Hopefully you can avoid the mistake. All right? This one, no. It's more like a category error. A relation should be a set. This is not even a set. You don't even need to look at that. No. And then I'll build this up. No. Not even a set. Okay, second one. Now let's give you a set. A relation on S1 and S2. Is this a relation on those 2 sets? Again, I meant every character I wrote. Monica?
I think the elements in the first set.
So, say it again.
The elements in S1 could come first.
Ah, yes. Remember, a relation is a set of pairs. A pair is where the elements order matters. Here, when we say it's a relation on S1 and also S2, that means implicitly every member in the relation should really come from some element drawn from here, for example here, and followed by another element drawn from here. Somehow I say B and 2. No, not good. The order is wrong. All right? This one here is a set, but S1 element should come first. should come first in the ordered pair. Sounds so good? You know, it's really sometimes even the basic, maybe this is most challenging to really clarify. But once we do that, once we get more advanced, it's more straightforward. All right? Another one is 1A, 3B, a relation on S1 and S2. Again, I meant every character I wrote. Yes or no? You're kind of afraid to say yes anymore, right?
Yes.
This one, yes? Are you sure? 100%? No error? Good. It is. Very good. This is a typical one. Okay? Because you can see it's a set of pairs, and 1 and 3 came from this set. A and B came from over here. That's a very informal way to decide. We're going to define that more formally later. Okay, so these are just warm-up exercises before I ask you a very important, two very important questions, right? Number one. What would be the minimum relation on S1 and S2? Number two, what would be the maximum relation on S2 and S1? You can think about the one we just did over here is neither minimum nor maximum. It's somewhere in between. But let's now figure out the extreme cases, and then we will be able to enumerate all the relations, like how we enumerated power set, pretty much. That's where we're going. Okay, minimum and also maximum. What will be the minimum relation? Again, you got to go back to the very first line for definition. A relation is just a set of pairs. What will be the minimum relation? Should be a one element relation or even smaller. Empty, indeed. Empty set, funny enough, is also called an empty relation in this context. Right? Number one. Empty set. It's called empty relation. You can think about for any given S1 and S2, the minimum relation on these two sets is always the empty relation, always. All right? And what about the maximum? And you have to use, a little hint, you have to use what we just covered maybe about 20 minutes ago, or maybe something like that. Yes, go ahead. Yes, exactly. You got to use the cross product. Because you want to figure out exactly how to enumerate all the order pairs between S1 and S2. And the way to do it will be cross product. Ryan.
Did you write S2 and S1?
S2 and S1 and S, yeah, sorry. The order definitely matters. And it was just a typo. In that way, I didn't really mean every character I wrote, apparently, right? S1 and S2. Good. Thank you. Guys, thank you so much. Be careful with what I wrote. Go ahead, Edmund. Which one, sorry? Empty relation, yep. Oh, that's a good one here. Good question. Very good question. I'm going to write it down because it's so important. Well, Edmund's question here was, should it be this or this? Or does it matter? I'll give you a choice. One here, two here. One or two, or one and two, or neither. Well, cannot be neither. It's got to be one of them, right? 2, why is 1 wrong? Conceptually, what's happening here is like this. Let me write the second one, first one a little bit differently. Think about this one here is saying empty set where just empty set. Well, think about it's a set where there's only one relation that's inside. That's not what we're talking about. We're talking about a single relation that's the minimum. We're not talking about a relation. That's different. Okay, good. Think about this guy here is the empty relation. Okay, so this one is not the way to go. So this one is the way to go. It's like an empty relation with nothing inside. And the maximum relation will be just S1 cross product S2. Because we can draw the different combinations from S1 and S2. Question? Yes? Sorry, can you say that again? I didn't quite catch you. Empty set? You mean are you talking about the empty relation or S1 or S2 being empty? In a set? Okay. Empty set, comma, empty set. Oh, let me try to write down what are you trying to say empty set followed by empty set? Is that what you meant, or?
Yes, just that 1 comma.
This one here actually wouldn't work. You know what, how about it? Let me clarify with you maybe after class. Maybe something I'm not exactly understanding you correctly. Okay, so I wouldn't confuse everybody else. They're already having some hard time, I guess. It's confusing. Guys, it's confusing, but you gotta get it through. Otherwise, you'll suffer even more in the exam. Please, okay? So we know about the minimum, we know about the maximum. Now the next task will be, got a little bit of time, is to enumerate all the possible relations. Okay, we got empty relation, which is always a minimum. I had a slightly outdated version I'm presenting, but I already updated the slides a bit. I'll make sure I post it today, okay? But it's okay. But that's the minimum, that's the maximum. And this is just somewhere in between. And I'll give you guys a little exercise mentally, okay? Take a look at this set over here. We're using a set comprehension notation here. We're saying all the pairs xy such that xy should be in the cross product of S and T. And then we say x is not equal to 1. So it's not exactly the maximum relation, but with some restriction over there. Okay, guys, try to really convince yourself this set comprehension notation here can really be evaluated into this set over here. You can see there is not any element in the resulting set where x is equal to 1, right? 2 and 3. That's how we excluded that. Take a look at this example here and make sure you understand that. So we can now talk about relation. Okay? All right, the next one. And we're going to use the power set operator to express the set of all possible relations on S and T. Why? Okay, that's something we need to understand very well. Okay? Let's now do a little bit of sketching here, and then it's also set on the slides, right? Let's get this part very clear. Let's say we are given 2 sets. Given 2 sets, S and T. All right? Let's review what we just know. Minimum relation, empty relation. Maximum relation, S cross product T. That's what we know. And we want to figure out the entire range of possible relations that can be drawn from S and T. Okay? Let's say this is what we want. All possible relations that can be on S and T, right? Please. Okay. Okay, we want to get all the relations on S and T, right? It's going to be, okay, let's sketch this idea a little bit. Let's say the set of all possible. Each relation is going to be a set. So when we try to derive this particular set, it's going to be a set of sets. Okay? All right, let's try the following. We know that every member in this particular set is going to be a relation. Each member in this set is a relation. We know some of them already. Why don't we write them out? Empty relation should be there. And also, S cross product T, the also be there. I hope you will. What about in between? Any idea? If you try to see the way I'm trying to enumerate things, isn't that kind of similar to something we did before? Power set. Think about it, right? I'm trying to make some connection to you. That's why I said it's so important to understand power set, right? Let me try to recap and then give you guys a little bit of time to think about, and I'll give you the answer, okay? Our idea, it would be to enumerate all the possible relations that can be drawn from S and T, the two sets. We already learned from the previous page over here, inside this particular set over here, every member is a relation. The minimum one will be empty relation. The maximum one will be the relation that's simply the cross product between S and T. What about in between? What would be the systematic way to enumerate? Should we enumerate based on certain criteria, right? So we can enumerate one after another. On the cardinality of the relation, exactly. That's what we're going to do, all right? So think about what we're doing here. So this guy here is a relation of cardinality 1. And notice one thing here. It seems like we haven't really defined the cardinality on a relation, right? Actually, we did, because relation is a set. So when we say cardinality of a relation, we are saying the cardinality of that set of pairs, right? Cardinality, I definitely meant to say 0, for sure. And guys, what about this? This will be a single relation of cardinality what? 2 to the power of, maybe too much. Maybe too much. This will be the maximum relation, right? Isn't that something we talked about before? Let me remind you, just to convince you. Okay? Review that definition. I wouldn't expect you guys too much to really grasp everything. So this one here would be of cardinality S multiplied by T. Oh, sorry. And over here, you got to go for cardinality 1, cardinality 2, all the way to cardinality, of course, -1, right? All the way. That will be the conceptual idea, how you can enumerate relations.
Why did it go from 1 to S times T minus 1, not S times T?
Because S times T is already covered here, right?
Oh, okay, yeah.
I'm talking about the middle box over here.
Okay.
I'm already excluding this one and here's one. That's why. Yeah.
Then that would do it. Okay.
Good. All right. All right, guys. I think that's good. Let me just use 1 more minute. I know I'm running out of time. I think it's really important for you to understand this foundation here, because once we get to relational operation, we'll go much faster. All right. So what should you do? I would suggest do one thing here. And go over this slide here. I'm going to do that again, also with you on Thursday. And then try not to look at the answer here. Can you enumerate this relation? I'll do it together with you on Thursday, but you may just want to do it by yourself to see where you might get stuck, right? Don't think I'm not going to put something like this on the written test for exam. I might, all right? Thank you so much, and then I will see you on Thursday, all right?